Today we're on page 1 of our second chapter 5 notes packet, starting with section 5.8. We're actually going to cover pages 1 through 5. Up until this point in chapter 5, we've solved quadratic equations, equations of degree 2. Now we're going to solve higher degree polynomial equations. The graph of a polynomial function f of x equals x cubed minus 3x squared minus 4x plus 12 is shown below. Here you have it. We know the real roots, or the zeros, are the x-coordinates of the x-intercepts. A polynomial of degree 3, which is also known as a cubic, can either have 1 or 3 real roots. This function has 3 real roots because it intersects the x-axis at 3 different points. The graph appears to intersect the x-axis at -2, +2, and 3. We can tell for sure by entering the function into y equals in the graphing calculator and calculate the zeros. We can also find the roots, or the zeros, algebraically by factoring, setting each factor to 0 and solving for x. Sometimes the quadratic formula, or complete the square, is required if the quadratic factor is not factorable. So let's take a look at solving this algebraically. Third degree or cubic functions can often be factored by grouping, as in this example. We have f of x equals x cubed minus 3x squared minus 4x plus 12. Replace f of x with 0. So now we have 4 terms. So think grouping. There's no GCF, right? So we draw a line after the second term, write down the operation that follows. Now what's common to the first 2 terms, x to the third minus 3x squared, they have x squared in common. Factor out x squared, and we have x minus 3 as our other factor. Now look at 4x plus 12. What's common to 4x and 12 is 4. Now we brought out the negative already, so we're actually factoring out -4, and the other factor would be x minus 3. What's in parentheses should match as it does, so x minus 3 is one factor. What's left outside of parentheses, x squared minus 4 is the other. But we're not done yet, right? This is dots, the difference of 2 squares, so this factors further into x plus 2 times x minus 2 equals 0. Now set each factor equal to 0. And solve individually. So x equals 3, subtracting 2, x equals -2, adding 2, x equals 2. So there we have our 3 solutions, our 3 values for x, 3, -2, and 2. Next example. Sometimes cubic functions have only one real root, as shown in the example below. As we can see, it intersects the x-axis at just one point. There is only one x-intercept, the other 2 roots are imaginary. The only x-intercept or real root is x equals 2. The other 2 imaginary roots can only be found algebraically, so we wouldn't be able to find these roots graphically. We have f of x equals x to the third minus 2x squared plus x minus 2. Replacing f of x with 0. And again, we'll go about factoring this. There are 4 terms, so we're grouping again. Draw the line after the second term. Copy down the operation that follows. Now what's common to x to the third minus 2x squared is x squared. X squared factors out, our other factor is x minus 2. And what's common to x and -2 is simply 1. So we'll write 1, and our factor is x minus 2. What's in parentheses, x minus 2 is one factor. What's outside, the x squared plus 1 is our other. Set each factor equal to 0. Right, x squared plus 1 cannot be factored further, so we set our factor is equal to 0. Add 2 to both sides, x equals 2. Subtract 1, x squared would equal negative 1. And then recall, what do? Square root both sides. So x equals, whenever we compose square root, don't forget, plus or minus, and the square root of negative 1 is equivalent to I. So there we have our real root and our two imaginary roots. Next, in the following example, it appears from the graph that a cubic function has two real roots because there are two x-intercepts. However, at the x-intercept of the turning point of the graph at x equals negative 1, the root is repeated, or called a double root. This can be shown algebraically. So let's take this cubic equation, replacing f of x with 0, and again factoring. 4 terms, so we're using grouping. Copy down the subtraction. What's common? GCF here is x squared. X plus 1 is the other factor. And what's common to x and 1 is 1. Again, but we're taking out a negative 1. So our other factor is x plus 1. What's in parentheses matches as it should. X plus 1 is one root. And then what's outside, the x squared minus 1. Excuse me, it's not one root, is the other factor. X squared minus 1 can factor further, that is dots, the difference of two squares. So it factors into x plus 1 times x minus 1. So there we have our three factors. It's factored completely. Set each one equal to 0. And you can skip that step. I'm going right to the answer. So x would equal negative 1, x would equal negative 1 again, and x equals positive 1. So there we have three real roots. It's simply that the negative 1 root is repeated. It's called a double root. Next, for practice, right, find all roots of the following polynomial functions by factoring, use the quadratic formula, or complete the square. Check your solutions graphically. All right. And I know some of you do not have a graphing calculator at home, but if you do key them into the calculator if you would to check them. All right. We'll take f of x, replace it with 0, equals negative 2x to the third plus 6x squared minus x plus 3. I always like to start off with a lead coefficient that's positive, but let's say we leave it as it is. We're grouping. Whoops. Let's draw the line after 6x squared, okay, and copy down the subtraction. What's common here? Well, I could take out 2, or I could take out negative 2. Suppose I take out negative 2x squared. And then in parentheses, I'll have x plus 3. And here, what's common is 1. I'm actually factoring out negative 1, so I'll have x minus 3. And hopefully you caught me. If I take out negative 2x squared from negative 2x to the third plus 6x, that'll leave me with an x minus 3. Yes, now that's correct. And these match as they should. So x minus 3 is one factor, and that what's left outside, negative 2x squared minus 1, is the other factor. Let's set each factor equal to 0. And solve. X equals 3, add 1, and divide by negative 2. X squared equals negative 1/2. Got a bit of work to do yet. Now square root both sides. So we have x equals plus or minus. I'm going to pull out the negative. I square root of 1 over 2. We need to rationalize that denominator, so let's bring that up to a 4 by multiplying by 1 in the form of 2 over 2. And we have x equals plus or minus I square root of 2 over 2. So we here have our one real root and now two imaginary. So if we were to check the solution graphically, we would see that our graph crosses the x-axis at just 1 point. Next, number 2, replace f of x with 0. 0 equals x to the 5th minus x to the 4th minus 2x to the 3rd. Degree 5 here. GCF, x to the 3rd. Factor out the GCF of x to the 3rd, and we get x squared minus x minus 2. Look at the trinomial in parentheses. Can we factor that? Are there factors of -2 that add to -1? Yes, -2 and 1. So this factors into x minus 2 times x plus 1. Set each factor equal to 0. X cubed equals 0, x minus 2 equals 0, x plus 1 equals 0. Cube root both sides, you're still going to get x equals 0. Add 2 to both sides, x equals 2, and subtract 1, x equals -1. So we have 3 real roots. And let me just quickly key this into the calculator, show you what it looks like. All right. Okay, so when the lights went out, I took the time to key it in and press graph, and this is what we get for number 2. We would have to work on adjusting the window, but we'll have practice with that in class, not tomorrow, then the day after. All right, but there are 3 real roots. If we look at our table, we would see at -1, 0. So an x value of -1, also 0, and 2 produce real roots. Next, factoring and solving 4th degree trinomial in quadratic form. If you're given a 4th degree trinomial, highest exponent is 4. In this form, ax to the 4th plus bx squared plus c with no GCF, you can approach it like it's a quadratic trinomial ax squared plus bx plus c. The only difference is instead of writing an x in parentheses, you write an x squared. For example, to factor the trinomial x to the 4th minus 13x squared plus 36, you approach it like you're factoring x squared minus 13x plus 36. In other words, you go to the constant. What are the factors of 36 that add to -13? -9 and -4. And then we would write x minus 4 times x minus 9, but instead we'll write x squared minus 4, x squared minus 9. Then each quadratic factor can be factored, as in the given case. So the result of the factoring is going to be, right, these are both dots. So the x squared minus 4 would factor further into x plus 2 times x minus 2, and the x squared minus 9 into x plus 3 times x minus 3. Solving factorable 4th degree polynomials. A 4th degree polynomial has up to 4 real roots. You can find them graphically by finding the x-intercepts, or algebraically by setting each factor equal to 0. A 4th degree polynomial may have 2 real roots and 2 imaginary, or it may have 4 imaginary roots. In total, however, 4th degree polynomials have a total of 4 roots, real and or imaginary. Imaginary roots can only be found algebraically. Real roots may be repeated if the x-intercept is at a turning point of the graph. So looking at examples of fourth degree polynomial functions. We have f of x equals x to the fourth minus 13x squared plus 36. Replace f of x with 0. And let's go about factoring. All right, it is a trinomial. Even though it's of degree 4, we go to the constant. The factors of 36 that add to negative 13. This was from the other page. Negative 9 and negative 4. So this would factor into x squared minus 9 and x squared minus 4. Which factor further? Both are dots. X plus 3 times x minus 3 and x plus 2 times x minus 2. You would set each factor equal to 0. Again, usually we skip this part, as I almost just did right there. Minus 3 equals 0, and solve them. So x equals negative 3, x equals 3, x equals negative 2, and x equals 2. And the graph is already done for us, and you'll see that we have our 4 points of intersection with our graph and our x-axis. So the x-coordinates there, negative 3, negative 2, 2, and 3, are our real solutions. Next, replace f of x here in number 2 with 0, and let's go about factoring. The factors of 16 that add to negative 8 are negative 4 and negative 4. So we have x squared minus 4 times x squared minus 4 equals 0. Factor each difference of perfect squares. X plus 2 times x minus 2. X plus 2 times x minus 2 again. Setting each equal to 0 and solving. Skipping the setting equal to 0, go right to solving. X equals negative 2, x equals positive 2. X equals negative 2, x equals positive 2. So the negative 2 and positive 2 are what we call repeated roots. Three. 0 is equal to x to the fourth plus 5x squared plus 4. The trinomial, let's go to the constant. The factors of 4 that add to 5 are 4 and 1. So this factors into x squared plus 4 times x squared plus 1 equals 0. Set each factor equal to 0 because these cannot factor further. They're not difference of two squares. They are sum. Subtract 4. X squared equals negative 4 and square root both sides. So x equals, simplify the square root of negative 4. That's plus or minus 2i. Subtract 1. X squared equals negative 1. Square root both sides. X equals plus or minus, simplifying the square root of negative 1. That's I. So our roots here are imaginary. There are no real roots. We have x equals plus or minus 2i and x equals plus or minus I. And the graph is shown for us. And you see that our graph does not intersect the x-axis, so it has no real roots. And on page 5, the top of page 5, I'm going to ask you if you would do, well, let's do number 4 together, and then we'll say number 5 we'll do together in class the next day. Okay, so x to the fourth minus 81. Factors of negative 81 that add to 0, right, are going to be negative 9 and positive 9, where, of course, you recognize that as a difference of perfect squares. X squared minus 9 times x squared plus 9 equals 0. The x squared minus 9 factors further into x plus 3 times x minus 3. X squared plus 9 does not factor any further. Set each equal to 0, x equals negative 3, x equals positive 3, x squared plus 9 equals 0, and need to solve that. Subtract 9 from both sides, x squared equals negative 9. Square root both sides, and x equals plus or minus 3i. So here we have 2 real roots and 2 imaginary. And we see that our x-intercepts here are just 2 of them at negative 3 and positive 3. And we'll save number 5. We'll start off with number 5 in class tomorrow. This concludes our notes for tonight.